Yet, and one of the main reasons is because weather is a big challenge. And because of the emerging technology, we need rapid testing, and outdoor data collection sometimes can be slow, that we have to wait for the certain type of weather, and
data center. So moving forward with the motivation and why this research matters. So it is very important for autonomous vehicles to precisely understand the driving environment, which ensures safety for both the vehicle and the surrounding traffic. The goal of this particular research is to achieve the centimeter level accuracy in estimating the vehicle's lateral position with respect to the lane center. This again ensures safer autonomous driving and vehicle maneuvering, and also for applications like the vehicle following applications. So the other key aspect of this particular research is energy efficiency, where implementing a system which can accurately estimate the lateral offset can help with reducing the aerodynamic drag, which again improves the fuel efficiency in vehicle following applications. Also, accurate lane positioning is critical for level 4 and level 5 autonomous vehicles, where the vehicle itself has to do the almost all the control of the autonomous driving with minimal human intervention. So this particular illustration in this slide, down the slide, shows the actual working of the project, where consider an ego vehicle, the blue card is following the lead vehicle, the red card, where this particular system accurately estimates the offset, which is the red line that you could see near the blue card, like in front of the blue card, and it helps in performing the steering control for the offset correction, which makes sure the vehicle stays within the lane. Yeah. So moving forward with the methodology, so how practical this particular system works. So starting with the Z camera, which is being mounted on top of the driver's head for better lane visibility, where this particular image is being downsampled to 360 cross 720 pixels for higher performance. So this image being collected is first passed into the computer vision core, where the YOLO V8, custom YOLO V8 segmentation takes place. So this custom YOLO V8 segmentation provides an output of the safe lane boundary within the lane, the actual lane, which actually tells the safe driving area. So this particular model is being built on driver's dataset. So once the lane segmented area is being detected, it moved forwards with the novelty of this particular research, which is the actual offset estimation. This particular research, I have built a 9-point calibration method, which provides a centimeter level offset estimation with respect to the lane center. So once the offset is being calculated, it is being communicated to the autonomy core via UDP interface, low latency and real-time processing. And then the autonomy core performs the actual speed and steering control, which helps the autonomous vehicle to stay within the lane and maintain a safe position. So moving forward with the first lane, the YOLO V8 lane detection model. So this model has been, to make sure this model is robust for real-time situations, it has been built with around 5,000 plus images, which has been collected in various challenging driving scenarios. To make the model more robust and work effectively in real time, the images being collected includes diverse weather and lighting conditions like normal daylight, underexposed scenes, snowy roads, foggy environment, and nighttime driving too. So to make the model more robust and adaptable to the real-time processing, some of the pre-processing and argumentations have been made. So argumentations like pre-processing includes auto-orienting of images, which is just to make sure that images are consistent throughout the dataset. And then argumentations includes variations in hue, saturation, brightness, exposure, blur, and noise. So this particular argumentations make sure that the model is capable of learning to the environmental variations that actually happens in the real-world driving situations. So moving forward with the training performance of the model. So if you could see the first left 4 graphs, like you could see that the model, the loss curves, you could see a consistent downward trend across all the loss metrics, which clearly shows that the model is learning good, and also the steady convergence with the decreasing loss shows that the model is learning well to segment the actual lane within the lane limit. Now, if you look up the validation curves, where you could closely see that it tries to mirror the training curves, but still you could see small jumps, which is the actual representation of the minimal overfitting, and also a strong generalization towards the diverse other environment data set. So the next process of the actual lane calibration and the offset estimation is depend on this particular lane segmentation. So it is very important to make sure this particular lane detection is reliable, to make sure we get a precise offset estimation. So if you could see the metrics, the precision recall score, which is almost very good, so which clearly shows that the model is capable of segmenting the safe limit within the lane line, and also the other metrics which shows that the accuracy of the segmentation with respect to the labels that is being labeled. Yeah. So moving forward with the calibration process. So this calibration process is basically to convert the lane segment, which has been detected in the image, into the image, like converting the image metrics into the real world measurements. So so we have used 9 reference points, which corresponds to 3 for the left edge, 3 for the center line, and 3 for the right edge. While doing this calibration, we also made sure that zero steering in the wheel reference to make sure the perfect edge of the vehicles. So if you could see the top view in the bottom, which actually represents the 9 points which is being placed in front of the vehicle, and also the front view shows how the points are actually being placed for the calibration purpose, and the camera frame, which has a couple of variables which I will be explaining you guys later. So this offset estimation has a couple of steps to be followed, starting with fitting the regression line on the calibration points. So 3 regression lines, LL, LC, and LR are being fitted with respect to the left, center, and the right calibration points. So the next step will be choosing a reference lane. So choosing the reference lane is one of the key for this particular calculation, where if you could see this image, the line LH1 is the actual reference line, which has the edges, the left and right end, PLH1 and PRH1. So the distance between PLH1 and PRH1 is the actual width of the lane, and the central point, which is being denoted in the yellow, which is PCH1, which is the actual lane center. So this particular reference lane can be represented in this slope-intercept form with the mathematical equation being shown in this slide. Also, moving forward, the next step will be predicting the intersection points, calculating the intersection points. So these intersection points are the points between the regression lines and the reference line. So the point PL corresponds to the intersection between the regression line of the left edge of the vehicle and the reference line LH1. Similarly, PC and PR are the intersection points corresponds to the center of the vehicle and the right of the vehicle. So here comes the actual distance calculation. So first, we actually calculate the distance between the intersection points and the actual lane center, which is the PC of H1. So DC is the distance between the intersection point PC and the lane center. DR is the distance between the intersection point PR and the lane center. DL is the distance between the intersection point PL and the lane center. So next comes the offset calculation in pixels. So with respect to the distance calculated previously, we just calculate the offset, which is the difference between, so to be very practical, this yellow point is the actual lane center, and this PC intersection point is the center of the vehicle. So ultimately the distance between these 2 points is being denoted as the offset in pixels. To be more accurate, we are also considering the left and right intersection points with the actual distance that we have done with respect to the calibration. So the final offset calculation in pixels is nothing but the average of all three values, which makes this value to be more accurate. So next comes converting the offset in pixels to the real world measurement, which is meters. So for the pixel to meter conversion, we have considered the standard lane width, which is 3.6 meters. So this mathematical equation here represents the equation where d cap MOH1 will be the final offset which is being calculated in meters, so this d cap POH1 will be the offset which is being calculated in pixels, and the element DLR is nothing but the pixel distance between the left and the right edges of the reference lane. So we get the reference lane of, to make this calculation more accurate and robust, we consider multiple reference lanes inside the segmented area to make sure the offset calculation corresponds to the small minor changes on the segmented output, maybe a small curvature of the road and things like that. So considering multiple reference lines, so this particular offset estimation is being calculated for every reference line that is being considered, and the average of all the reference line is being found to be the final offset calculation in meters. So coming to the model assessment and implementation, so this particular model is being implemented in MDU's connected and autonomous vehicle, which is being tested in the tracks of American Center of Mobility. So during the evaluation, our concentration was towards two key things. One was the lane detection model, and the other was the offset measurement accuracy. So if you could see the image here, so this is how the final output visualization will be, where this green segmented area is the actual safe limit which we got from the lane segmentation model, and the offset which is being calculated with a centimeter level accuracy, which also sends the signal to the autonomy core to make the movement to stay within the lane. So talking about the platform that is being used to evaluate this particular system, where we used MDU's L4 and level 4 and level 5 capable connected autonomous vehicle, which has like number of sensors like the LiDAR, the high accuracy, low metal GPS, DSRC, cellular WCX for communication and things. And also talking about internal things, the next mission for the entire autonomy core control, the Myco auto box and new vehicle drive-by-wire for the precise vehicle control, and the very stable power distribution with CAN converters and things, which helps for the proper operation of the vehicle. So this particular sophisticated platform helped us to evaluate the actual efficiency of the system in comparable to the real-time performance in real-world situations. So now first talking about the lane detection model performance. So we tested this model with another 200 images collected from different situations which were not included during the part of training. So you could see that the top row of images is the actual label which we need, and this will be the actual the predicted output of the lane segmentation model. As you could see that in this image, the road is there is not even a proper lane on the road, but still the model manages to estimate the safe limit area. That is because of the methodology that is being used during the labeling, where I considered all the cracks in the roads, the color contrast in the roads, and things like that to make sure I get a decent lane, which is of a closer accuracy. So the metrics clearly shows that the model is performing very good in estimating the lane, safe limit lane inside the lane boundaries. But still, this model is not the normality of the research. But still, we have to make sure the model to be more reliable so that we get a better precise offset estimation. So next comes the centerline estimation model analysis, where we use GPS signals with RTK corrections on HTML roads as ground truth in comparing with the real-time offset calculated by the model. So we conducted 3 different trials on roads, which is swinging left and right to make sure we get a decent variety of road conditions, and also making sure that we get a variety of centerlines so that we can actually access the performance of the model. So on the test one, you could see the regression plots in the right side, where we got a positive correlation between the error calculated and the true offset of the ground truth with a slope of 0.4, so which is again a positive correlation between the elements. And then which is very much clear that the model underestimates the offset, the real offset, where you would see like most of the points are close to 1 meter offset, which is okay, but not very bad. So, and also to remove the systematic errors, the linear trend, we introduced something called as the degenerate error, where which is being represented with this mathematical equation, where each row is the actual error difference between the calculated offset and the ground truth with respect to the GPS. D-cap is the actual distance estimated by the model, when I and S are the intercept and slope. So the histogram plot shown below, which clearly shows that it is a zero mean distribution, where we get a standard deviation of 0.166, which is nothing but the random walk error. So talking about the test 2, we tried a similar road where we got a slope of 0.35, which is better than the test 1, but still the model underestimates the real-time offset, like the true values. So underestimation persists. And also talking about the degenerate error, the standard deviation was around 0.1, which is better than the last test. So which shows the less variance in the error distribution than test 1. So next comes the GPS-based offset to centerline estimation for the test 3, where we got a slope of 0.27, where you could see the points are mostly close towards the 0.5 meters offset, true offset in the error. So here again, the similar underestimation trend is being observed as similar to the previous test 1 and 2. And also talking about the degenerate error, the standard deviation is 0.107, which is nothing but the random walk that we'll be considering in the later stage. So summary of the model result. So the source of the basic bias error where the GPS data inaccuracies were within the range of 0.2 to 0.5 meters, which is pretty okay, and also some of the model estimation errors that gave the actual bias error. So we considered, based on the previous 3 tests, we considered 3 main variables which are to be included in the final error model, which are the E-scale, E-bias, and the E-random walk. So the final E-scale that we got is 0.328 meters, the final E-bias is 0.214 meters, and the random walk is a normal distribution between 0 and 0.135. So this is how the entire system works. So after the offset calibration model estimates the offset value, the centimeter level offset value, we perform including this fine-tuned error variables which sharpen the final offset value to get a better result of offset estimation. So this will be the final mathematical equation where d bar is the final value of the offset calculated considering the error terms. D true is the actual offset which is being calculated from out of the calibration model, and considering E scale and E bias for a standard better accurate value. So conclusion, so we achieved an accurate and a real-time model using a custom YOLO V8 and the novel offset estimation. We achieved offset like centimeter level accuracy in estimating the offset, And also this particular system being tested with NVIDIA Jetson HX Orin gives a decent performance of nearly 30 FPS, which is okay for real-time performance. And most probably the other important thing about the model, it handles poor road lane markings in very road situations. Also the 9-point offset calibration ensures precise offset estimation, also which improves the overall performance of the vehicle and models like the vehicle following applications. So, talking about the future work, so we are planning to consider testing this model on complex roads with sharp curves and multi-lane conditions, and also we are trying to include lane maneuvers. And also we are planning to incorporate other sensors like LiDAR for dynamic lane width estimation, which is being used for the final offset calculation from pixels to real-world metrics. And also we are trying to continuously work on optimizing the model performance for real-time autonomous deployment. Yeah. So acknowledgements. So as I said before, this project is being funded by the US Department of Energy, the Alpine XCAR project, and several other industry partners like Stellantis, GM, others. So thanks to my mentors and advisors, Dr. Neighbor, Dr. Dial, Dr. Mustafa, and Aman, and all the team of APS Labs. Yeah, thank you. Any questions?
So I saw that you have a 99.5% accuracy.
Yes.
And in the context of autonomous driving is full autonomy, what would be the reliable percentage of detection?
Talking about this particular work, we actually, so our novelty is not towards the actual lane segmentation. So we didn't put much of the concentration towards the real-time analysis. So what we just did is we basically considered 200 random images, and we just evaluated the model to put an extra word that this model is working good, and also it supports the next step of the model, which is the actual offset estimation. So maybe in future work, we will consider evaluating the model in real-time situations. Yes.
You say it says there's one that didn't work. Do you have that image, and what about that case?
So I think I remember what that image was. So it was a brightest image with all the lane very dark. So yeah, it was one of the difficulty when it comes to image processing, where getting the camera and the system, which is very much calibrated towards the sudden environmental changes, is a bit difficult. So maybe like we can use other complicated sensors like LiDAR and things to overcome this problem.
So it'd be like a case where you're driving into the sun, where it's low on the horizon during sunset or sunrise. Yeah. Okay.
Any other questions?
Maybe I missed it. Did you test it for adverse weather like rain, fog, snow?
So for the offset estimation or the lane detection?
Lane detection.
So yeah, so this image has like the 200 images that I considered actually had some of the images with some snowy conditions, like there are roads which are partially covered with snow, but still it was not severe weather conditions. So maybe like in my future work, I would include that. Any other questions? Okay, thank you.
Very good. I have to head back to